Okay, so let's see what we can conclude about the origin of the force that's making this current. What do we mean by that? I mean, we know that we just said that there's going to be a current in the previous video. Experimental observation says if you move the permanent magnet upwards towards this loop, the loop itself has no way to make a current on its own. So the current somehow is being generated in this loop by the movement of this magnet upwards. So there's some current in this direction. Remember, current doesn't have a direction. Current is a scalar. So actually what we mean by this direction is the direction of J. And with the charges that can move in the wire that make the current are negative charges. So of course for negative charges, if you go back to the chapter on current, the negative charges, the velocity of them is opposite the direction of J. So if the direction of the current is this way, the way in this arrow, then the velocity is this way. So there must be some force being applied on these negative charges to move in this direction. Because remember, negative charges moving in the wire is full of other things that they're continuously hitting other things. They're continuously hitting other electrons, the atoms around in the molecules in the material. So they always continuously hit things and lose their energy, and then they have to gain that energy again by having some force being applied to them to increase their speed, and then they lose the energy again. Remember, resistive material or metal, it's full of particles. It's full of parts. So the electrons, as they're moving in them, they need to be continuously having a force applied to them to keep on producing a current. So the question is, what is the origin of this force that's trying to make the charges move in this direction? Let's think first of all, what is the total force acting on any charge? If you have a charge in space, what's the total force acting on it? We've taken this before already. The total force is QE, the force due to an electric field, or QV cross B, the force due to a magnetic field. So the question in this part is, which force do you think is the one that's responsible for making this current? Is it the electric force or the magnetic force? Think about it for a while and see what you come up with. So I'll tell you now that the charges were initially at rest. Let's say this loop was just fixed in space and the magnet is moving up towards it. And so initially the charges were not moving. But then you start moving the magnet up, and then you notice that there's a current. So that means the charges must have changed their speed. Initially they were at rest, and then they start to move. Remember we said before that the magnetic force is zero unless the charges have some speed. If the charges are at rest, then they cannot experience a magnetic force. So that's the case if the charges originally were at rest. Okay, let's say that the charges were moving in the wire and that there was some current. We can show that the magnetic force on those charges is always perpendicular to the velocity vector, and which means that it's perpendicular to the wire. So actually the magnetic force, if it exists, it's perpendicular to the direction of the wire. It's not along the wire. So it's not going to be a force that can make the charges flow in the wire. It has nothing to do with that. The magnetic force cannot make the charges move along the wire. So it's not the magnetic force that's responsible for making the current. If you want to just think about this, imagine looking at this loop from above, looking down. You see is the magnetic field coming towards you. This is the loop. And the charges that are moving in the wire, let's say this is the velocity vector. Remember, what's the magnetic force on a charge? Q V cross B. Now, V cross B is always perpendicular to V. Right? The cross product between two vectors is always perpendicular to each vector. So that means V cross B is perpendicular to this velocity. So the force is some vector that's perpendicular to the velocity vector. So this force, even if it exists, it's not the one that's responsible for making the charges move along the wire. So the conclusion is, it's not the magnetic force that's making the current flow in this wire. So the conclusion that we can find is that there must be some electric field that's created along the wire which is making a force on the charges. So there must be some electric field, and since the charge here is moving with a velocity this way, that means this electric field should be going this way, because remember, if this electric field behaves as an electric field, then the force on this electric field is Q times E, and if the charge is negative, then the electric field will be opposite the direction of the force. So if we want the charge to move with the force this way, then the electric field will be this way. So it must be that there's some electric field induced in this wire going this direction, and this electric field, it's a new kind of electric field, and that's what's responsible for making the force on this charge. This electric field, we give it a new name. It's called a non-conservative electric field, ENC, non-conservative. It's not the same as the one that we took before due to static charges, but nevertheless it's an electric field, in the sense that if you put a charge in the region where this electric field exists, it'll experience a force Q times E. So then we need to now try and find a law that will involve this new electric field and tell us how its value, how to get its value. Some kind of new law, and that's what we're going to discuss next, and see how we can find a theory that can explain how this non-conservative electric field is created and how much its value is. How can we calculate it?